Every time your phone finds a route through a city, every time a social network suggests a friend, every time a build system figures out what to compile first, there's a graph underneath. Graphs are the most flexible structure in computer science. Anything that's a set of things with connections between them is a graph. This is the start of a 5-part series. Today, what graphs are and how to store them. Formally, a graph is 2 sets. Vertices, the circles also called nodes, and edges, the lines connecting them. Here, A through F are vertices, and each line is an edge. 2 vertices joined by an edge are called neighbors or adjacent. The number of edges touching a vertex is its degree. A has degree 2, E has degree 3. That's the whole vocabulary, and everything else builds on it, things and the connections between them. Graphs come in a few flavors, and the distinctions matter. Edges can be undirected, where friendship goes both ways, or directed, like a one-way street or a follow on social media. Edges can carry weights, a distance, a cost, a capacity, or be unweighted. A graph with a cycle lets you loop back to where you started. One without any cycles is acyclic. A directed acyclic graph, or DAG, is special enough to earn its own name. It's how we model dependencies. Here's a directed graph. The arrows mean edges, now have a direction. In a directed graph, degree splits in 2. In degree counts the arrows coming in, out degree counts the arrows going out. This is also our first disconnected example. Notice the A, B, C cycle on the left can't reach D, and E on the right at all. A graph can come in separate pieces called connected components, and any serious algorithm has to handle that. How do we store a graph in code? 2 ways dominate. An adjacency list maps each vertex to the list of its neighbors, a dictionary of lists in Python. It's compact, and it's what you'll reach for most of the time. An adjacency matrix is a V by V grid, where cell I, J is 1 when an edge exists and 0 otherwise. Lookups are instant, but it always costs V squared space, even when the graph is nearly empty. So which one? It comes down to density. An adjacency list uses space proportional to V plus E, vertices plus edges, so it's ideal for sparse graphs, where most pairs aren't connected. That describes almost every real-world graph. A matrix uses V squared always, but it answers the question, is there an edge between X and Y in constant time versus scanning a list? Rule of thumb, list for sparse graphs, matrix for dense ones, or when you check specific edges constantly. Once you see graphs, you can't stop seeing them. Road networks and GPS routing. Social networks, with people as vertices and relationships as edges. The web itself, pages linked by hyperlinks, which is exactly what Google's PageRank runs on. Dependency graphs inside package managers and build tools. State machines, recommendation engines, even the neurons in a neural network. Master graphs, and a huge range of hard problems suddenly share a single toolkit. That's the foundation. Vertices, edges, and 2 ways to store them. But a graph is only useful if you can explore it. Next episode, we start walking it with breadth-first search, the algorithm that fans out level by level and finds the shortest path in an unweighted graph. That's where the color-coded animations begin.